and I'm very grateful to have the opportunity to be invited here and to speak in a workshop with so many distinguished colleagues. It only seems like a few weeks since the kickoff to the SAMC year, so I'm back again. And it's nice to be back in the Triangle too. I was here in the late 80s at NC State, and of course there have been many changes since then. Okay, so this is a topic that I've talked about quite a bit in the last couple of years, and the first part of my talk on coordinate descent methods is sort of describing where the theory is. The theory is comparatively recent, which is surprising for such an old class of methods, the convergence theory. I'll talk about different variants, the obvious one where you just cycle through the variables, and the randomized ones where you make some sort of random choice. And there are two versions of that, as I'll talk about. So that's the first part of the talk. Then the second part of the talk is stuff that I've done recently in the last, just in the last 6 months or so, on really trying to drill down into this issue of the random permutations variant, one of the random variants that's really not well understood and for which there isn't much theory. And so I've looked at a particular class of matrices where the random permutations variant differs from the cyclic variant, and you can explain why by doing a careful analysis. So that's the second part. All right, so here's the outline. So coordinate descent, I'll start by describing the different variants. I'll talk a little bit about the known convergence results. This is mostly stuff from the last 5 years or so, pretty recent. Just give us some snippets of computations that show the difference between the variants. And then, as I said, look more carefully at the random permutations form. And this is joint work with my student, Ching-Pei Li. Okay, so this is the basic coordinate descent framework. So here, I'm just talking mostly today actually about minimizing a smooth function f of x. So it's a smooth, in fact, convex function, right? This is like the easiest. You have to understand the easy problems before you can understand the hard problems. And it's hard to even understand the easy problems for this class of methods. So this looks a little bit complicated, but all that's happening is that at every iteration, we're picking one of the n components of x, and we're taking a step just in that component. So EI represents the basis vector for the ith component, and I'm choosing to describe the step as being some multiple of that same component of the gradient. So you take the ith component of the gradient vector, you multiply it by some step length alpha, and you just move in that direction. Okay, so that's the basic idea. Now the different variants are distinguished between different ways of choosing I. So I've organized the iterations here into two loops that sort of show up the difference between the variants. So the cyclic variant is the one where you just, on the inner loop, you cycle through the components in order from 1 to n. 1, 2, 3, 4 up to n, 1, 2, 3, 4 up to n. And so each L represents one epoch of computation, one complete cycle, one complete pass through the components. So that's the so-called CCD, or cyclic coordinate descent approach. The fully random approach you can think of as being a sampling with replacement. And there, every time you choose a component, you choose it completely independently and uniformly and independently of whatever's come before. So then you don't really need, for the fully random variant, you don't really need to organize it into epochs, but I just do that for uniformity with the other variants. So that's the second one that we'll talk about. And the third one is the random permutations variant, and that's the one where you do it one epoch at a time, but at the start of each inner loop, you reshuffle the n components. You just do a random shuffle of the n components, and then you work through them in the order that you shuffle them into. And so at each epoch, you reshuffle, and you work with a different permutation. So you can think of that as being sampling without replacement within each cycle. Okay, so in some sense, it gets a more guaranteed uniform coverage than a fully random variant. Okay. So other ways that you can differentiate between variants of coordinate descent is in the choice of step length. Obviously, most practical versions of coordinate descent actually work with blocks of variables at a time, not just a single component, but I'm not going to talk about that at all. And then there are this whole area of parallel coordinate descent. That's something that I've worked on, and Mike Jordan covered that yesterday as part of his discussion of parallel stochastic gradient and coordinate descent. And I'm not going to talk about that today. I'm really just drilling down on the very fundamental issues of the behavior, particularly of this last variant, random permutations. Okay, here's another extension that's very important when we come to do data analysis problems with coordinate descent, and that is often you have a regularization term added onto a loss function, and this regularization term often has a lot of structure. It's often convex, but not always, as came up in Fan's talk yesterday. He talked about MCP and SCAD, which are component-wise non-convex regularizers, and Martin Wainwright and Po-Ling Lo have also worked a lot on those topics. But a very important one is the L1 norm. That's used a lot in signal reconstruction and lasso and so on. So you can adapt coordinate descent to problems with this structure even when this function here is non-smooth. And the way that you do that is that you form a linear model of the smooth part, which is f. So you linearize its ith coordinate. You take a gradient first order model of what happens when you change the ith coordinate. You can add on this damping term, which is simply a quadratic sort of prox term weighted with 1 over alpha, and then you add on the ith component of this regularization function. I'm assuming that this regularization function is separable. You can express it as the sum of terms, each of which just depends on a single component. So this really is the form of coordinate descent. This is a little subproblem you have to solve to update the ith component of x. And when this has a simple form, like it's an absolute value coming from a 1 norm, you can solve this in closed form as well. And if this term is not there, then it just reduces to the usual formula. So a lot of the analysis has taken place in this context. And the convergence results mostly go through. Sometimes the complexities are not quite as strong as for the fully smooth case, but in principle it's not all that different. By the way that you solve this subproblem, this is such a commonly occurring subproblem in a lot of literature in this area that there's a name for the operator for the solution of this problem. It's just called the prox operator. And so you can express this subproblem as in this form, where this prox operator is defined by this little operation here. Okay. All right, so I won't say too much more about this. I'm just going to focus on the smooth case, but I wanted to mention that that in practice you often have this regularization term and you can deal with it. So back when I was preparing a survey talk in this area for ISMP last year, I just did a Google Scholar search on coordinate descent and coordinate relaxation and found a whole wealth of application areas where this sort of approach has been used. So the scientific literature is full of examples of where people have used this approach. It's a very intuitive approach in a lot of areas. So here's a summary. You can see they're from all over: medical physics, biology, gene expression, phase retrieval, crystallography, and so on. So they're all over the place. So, and some of this literature goes back 30 or 40 years. So it's a very old-fashioned approach. And one question you might want to ask right away is, why does it even make sense to do this? Because we've known for a long time that getting full gradients is not that expensive. So why don't you just compute a full gradient and do something like a steepest descent or a Nesterov acceleration or something in the case of a smooth function? So in fact, there are theorems that are coming from the automatic differentiation community, and this is maybe the most recent text on automatic or computational differentiation. There are theorems that say that if you've got a code that can evaluate a function f of x, that you can get the gradient for no more than about 5 times as much as it costs to evaluate the function. So given that the gradient's not expensive, why don't we just use that? Well, the answer is that in data analysis problems, like we're concerned with here, the premise is wrong. You can't actually get the function itself very cheaply. To calculate the loss function coming from a data set or a statistical model applied to a data set, you have to read the whole data set, and that's very expensive. So that's why algorithms like stochastic gradient are so popular, because you can make progress just based on a very small sample of the data. So the bottom line is here that f is expensive to solve, to calculate, which means that the gradient is expensive. So you might want a method that can make progress using a lot less information than a full gradient. So that's the motivation. Now, again, that only makes sense if it's cheap to compute, or relatively cheap to compute, a single component of the gradient rather than the full gradient. So is that true? Well, yes, it is. And I'll give you an example on the next slide of problems where that is true. Before we leave this slide, I just want to mention that another reason for doing coordinate descent is that it's easy to implement in a parallel asynchronous setting. And this And Michael Jordan mentioned this in his talk yesterday, and that's something that we've worked on as well. Okay, so here's an example of a problem where getting a single component of the gradient and making the required updates to the data structures and so on is a lot cheaper than getting the full gradient. And this is a very common kind of problem that arises in ERM or regression or classification problems. So this is a problem where the data is in this matrix A. It's an m by n matrix, and the function that you want to minimize consists of an empirical loss, this term, and a regularizer in the second term. Okay, so each term in the empirical loss depends on one row of the matrix A. So you take the jth row of the matrix A, operate on the vector x, which could be a weight vector or something, that's the vector of unknowns, and you get a scalar, aj.x is a scalar, and then you run it through a loss function here, so it could be a square, it could be a logistic regression or something, and so that's your function. So suppose you do enough bookkeeping that you keep track of a times x for the latest value of x. So you store this vector g, which has got the current value of ax, and suppose also you keep track of the gradient of hj with respect to each gj. So all of these are just scalars. So you keep track of those m scalars. Okay, so at the start of the kth iteration, that's what you know. Now suppose you choose to update the ik element of the vector x, you're going to need to know the ik element of the gradient. So let's see what kind of work you have to do to compute that. Well, you just have to look at the ik column of A, because that's the thing that touches the ik component of x, and you just have to sum up this formula. So you only need to look at the elements of the ik column of A that are not 0, and you just have to take those elements of the matrix A and multiply that by the appropriate entries from this vector here. So the amount of work you need to do that is only equal to about the number of non-zeros in the ik column of A. Okay? And then after you've done that, you have to, of course, update your vector g to reflect the change that you just made to xik, and that again costs about this much operations. It costs about the number of non-zeros in the ik column. So overall, the cost of one coordinate descent operation is about this much. Now, if you figure out how much it costs to evaluate the full gradient, that's going to cost you order of the number of non-zeros in all of the matrix A. Okay, so the expected amount of work on one iteration of coordinate descent is about 1 over n times the expected work of a full gradient step. Okay, so this is a scenario where it makes sense to consider coordinate descent as an alternative. Okay, so what do we know about convergence? So I'm going to talk, again, I'm just going to focus on the easy problems. So these are the problems where f is convex, and in fact I'm going to assume some sort of strong convexity property where it's bounded below by a quadratic, where the modulus of that quadratic is mu. In fact, it turns out that you don't really need that. You need a slightly weaker property that goes by a number of different names. We used to call it the strong property. There's another paper we call it essential strong convexity. It's actually a special case of Kerdyaev-Lovashevich property. And basically, it allows you to have a solution set that's not a single point. If you have a strongly convex function, the solution set's always just a single point. This doesn't require that. You can have a whole set of solutions, but as you move away from the solution set, the gradient has to increase at a reasonable rate. That's basically what this says. And if you've got this property, you get essentially the same convergence as for the strongly convex case. So you can think of this as being sort of a morally strongly convex type property. The interesting thing about this property is that if f is a convex quadratic, even if the Hessian is singular, it has this property. So it behaves like a strongly convex function, even though it's a degenerate function with an entire subspace of solutions. Okay. So, so in analyzing the convergence of coordinate descent, different variants of coordinate descent applied to strongly convex functions, functions with that PL property, we need a bunch of constants here. So there's the good old L, which is a Lipschitz constant for the gradient of f. And then there's a component-wise Lipschitz constant. This says what happens to the ith component of the gradient of f when we change the ith component of x. So we get a bunch of these sort of piecewise Lipschitz constants. And then L max is the maximum of all those. And these two things are not the same, but there is a bounded relationship between L and L max that I'll talk about. Okay, so There's a 2012 paper of Nesterov, I think it was written in 2010, but still pretty recent stuff, that analyzed the convergence of the fully random coordinate descent, where you're choosing the component to update IID at every iteration, sampling with replacement. And the argument is actually very elementary. You can show that the expected rate of improvement in the measure of non-optimality in the function, that is the difference between the latest function value and the optimal function value, the expected decrease in that quantity at each iteration is given by this expression here. So it depends on the smallest eigenvalue, it depends on n, the dimension, and it depends on L max. So if you look at what happens over one epoch, if you just aggregate that n times, take that quantity to the power n, and you get approximately this, okay, provided this quantity is small. Mu over L max is small. So if you can convert that into some sort of expected iteration complexity, how many iterations do you need to get a factor of epsilon decrease in the function, it's about this many. It's about L max over mu times log epsilon. Okay, so that's how many epochs of randomized coordinate descent you need. Nesterov actually has a slightly stronger result that gets a rate about twice as fast. It's an R-linear result. It's not guaranteed to get this on every iteration. There's a sort of extra, the constant has to be a little bit bigger, but you can go about twice as fast. Okay, so the first thing to think about is how does this convergence rate for randomized coordinate descent compare with the full gradient steepest descent, workhorse method, workhorse first order method for smooth optimization? Well, the very standard theory, and you can see this in, say, Nesterov's book from 2004 or many other sources, the standard theory for the amount of progress you make with one steepest descent step, if you use a step length of 1 over the Lipschitz constant, which is the classic step length, is about this much. You get this much decrease on one iteration of steepest descent. Now, I'm assuming that one iteration of steepest descent costs about as much as n steps of, or one epoch of randomized coordinate descent. So I can sort of do an apples to apples comparison by taking one epoch of coordinate descent and comparing it with one step of steepest descent. So we can compare this iteration complexity for steepest descent to the iteration complexity I got here for coordinate descent. It's very similar, except the L max has been replaced by L, okay? So we can compare the values of L and L max, and that gives us some indication of which one, has the better worst case complexity. So it turns out that the ratio of L to L max is bounded between 1 and n, and the L max is often smaller, all right? And that's good for coordinate descent because it means that the iteration complexity is smaller in general, okay? So right away it sort of makes sense to use this approach. In fact, the upper bound here, the upper bound of n, is achieved for quadratic functions by the case where the Hessian is just the matrix of all ones. Okay, then you actually get this upper bound. And we'll see that some of the examples that I analyze in the second part of the talk really have this property where L over L max is pretty big. So it does accurately predict the difference between, steepest descent and randomized coordinate descent, this ratio here. Okay, so that's maybe the simplest, the most elementary one of the three variants to analyze. What about cyclic coordinate descent? So this is one where you cycle through the indices in order. So there's a paper by Beck and Tetrashvili in 2013 in SIAM optimization, I believe. And its essential approach is that it treats cyclic coordinate descent as kind of a crude version of full steepest descent. So it relates the step that you take at any index I to what you would have taken if you'd evaluated the gradient at the start of the epoch, okay? You're actually doing better than that because at every step you're always using the very latest information about every component, but it sort of approximate that by a value of x that's actually a little bit outdated. And then it's able to use theory that's very much like the standard steepest descent theory. But they end up with rates like this. This is the rate for one epoch, and this is a deterministic. There's no expectation here because this is a deterministic algorithm. So you get about this factor of decrease in the non-optimality. Pretty ugly expression. It depends on your choice of step length, and they assume the step length is constant, alpha, and you recognize mu and L and so on. Paradoxically, if you do an exact line search, the rates get even worse, okay? So this was for fixed step lengths. So let's plug in some values of alpha and see what happens to that rate and see how it compares, say, with random coordinate descent and steepest descent. So here are some values, 1 over L max, that's the step length that you take for randomized coordinate descent. 1 over L is the steepest descent step length. And then there's this one that's even smaller, but it gives the best iteration complexity. So for all of these, the cyclic method seems to be slower. It's worse than randomized coordinate descent by this factor that depends on this ratio of L over L max and n. It's also dimension dependent. So it doesn't look very good according to that measure. It's also worse than steepest descent. And that is sort of counterintuitive because it should be better than steepest descent, because it's always using, it's doing one component at a time, always using the latest information, whereas steepest descent is stepping in all components at once. But in fact, the complexity, according to this analysis, looks worse. Okay, this was improved a little bit recently, at least in a special case. Yinyu Ye and Sun produced this report in May last year where they said that for convex quadratics, they could get a bound for steepest descent that looked like this. Now this is, again, very ugly. You'll see some new constants here, but these are simply the average value of the diagonals of the Hessian. This one here. This one's the minimum diagonal of the Hessian, so they're not too hard to define. But the main difference between this and the Beck-Tetraashvili bound is that the n here is turned into a log n, or a log n squared. So it's a little bit of an improvement. And this is for an exact line search. So it's considerably better than the previous analysis in the case of an exact line search. But again, pretty messy. And we'll return to this later when we talk about specific matrices. So I'll plug in a specific matrix later and get a more tractable value of that expression there. Okay, so here's the one that I'm really interested in, which is the random permutations case, where you shuffle at the start of each epoch, you just shuffle all the indices and then work through them in the shuffled order. There's pretty much no analysis for that before. You can apply the cyclic analysis without modification. If you just look at the proofs in Beck and Tetraashvili, they go through perfectly well if you assume that there's a shuffling at the start of every epoch. So you can bound the behavior of random permutations coordinate descent by the expressions for cyclic coordinate descent. However, it behaves much more like the fully random version in practice. It behaves, it tracks the random version much better than it does the cyclic version. Yet the analysis is only coming from the cyclic version. So what I really wanted to do here was to try to analyze the random permutation version in a way that actually proved that it was more like the random version. So to improve on the cyclic bounds, at least in some special cases. So that's what I was trying to do. Okay, so here's a few computations. I want to talk about convex quadratics because, again, I think you have to understand the easy problems first before you can really see what's happening on the hard problems. And you can argue that the easiest class of strongly convex smooth functions are convex quadratics. Okay, I guess pretty hard to argue with that. So, but we find that analyzing the behavior of these methods, even on convex quadratics, is actually really pretty tricky. But I guess that's not surprising because, as we all know, conjugate gradient method, analyzing its behavior on a convex quadratic is also very technical. There's an extremely rich, entire books have been written about the properties of conjugate gradient on a convex quadratic. So I guess it's not terrifying to know that even this case gets pretty tricky. And as I said, it's a good step towards understanding global convergence behavior. It hardly tells the whole story. So transitioning from convex quadratics to general convex functions is not obvious. The properties don't all carry over. And people who've worked on conjugate gradient know this well because many, many attempts have been made over the years to take linear conjugate gradient for convex quadratics and extend it to general functions. And there are many, many varieties of ways of doing that extension. And a lot of them don't work that well, right? Sometimes they work fine, but it's not, you certainly lose all the nice properties you get on quadratics. So quadratics don't tell the whole story, but it's a place to start. Okay, so I'm going to be focusing, I think, for pretty much the rest of the talk on this function here, x transpose ax, where A is symmetric, positive, semi-definite. I can put a linear term in there and just shift everything, but I don't lose any generality by leaving it out. And this one, we can write down what the solution is. Obviously, it's at 0. There might be, if it's semi-definite, if there are zero eigenvalues, there might be a whole subspace of solutions. But certainly the optimal objective is zero. And I'll start from some non-zero initial point. And I make this comment that it does always have the strong convexity type property, even if the matrix is singular. So we expect to see these sort of linear convergence rates that I've been talking about. Now, this obviously, if we do cyclic coordinate descent with an exact line search, that's exactly the Gauss-Seidel method, which I'll explain on the next few slides. And Gauss-Seidel is what everyone learns in their first numerical analysis course. And so we can think of the random versions with exact line search as being some sort of randomized Gauss-Seidel. Okay, so this analysis has relevance to linear algebra as well. It's known that you can sort of soup up Gauss-Seidel by overshooting the minimum at every step, and that gives you successive over-relaxation. And I won't talk any more about that, but the classical numerical analysis literature has, there's a lot of interest in analyzing these so-called fixed point iterations. And so what we're talking about here really is a very classical method. So here's the Gauss-Seidel connection. Expressing what Gauss-Seidel does, we can do that by just breaking down the matrix A into three parts. Strictly lower triangular part L, diagonal D, strictly upper triangular part L transpose. It's symmetric, so the strictly upper and lower triangular parts are just transposes of each other. Okay, and then what happens on one cycle of Gauss-Seidel, if you're just doing cyclic with no permutations, you can express what happens on one cycle by this closed form expression here. So you just take the L plus D part, you multiply it by L transpose, take the negative of that. That tells you exactly what happens to get from the x at the start of the epoch to the x at the end of the epoch. Okay, so you can write it down in closed form. So after L cycles, if you do no permutations, after L cycles you just get c to the L times the starting vector. So just a power of that matrix. And so the function value after L cycles is just given by that expression there. Okay, can you analyze that? Well, yes, you can. And the classical analysis of Gauss-Seidel and the numerical analysis literature does that. They show that if A is positive definite, that this matrix C, this one epoch operator, has all its eigenvalues less than 1 in absolute value. And so the long-term behavior of this iterative process, it behaves in the long run like the spectral radius of C. And so after L epochs, you expect to see a per epoch rate of about the square of the spectral radius, so something less than 1. So the classical theory guarantees convergence of the cyclic coordinate descent, otherwise known as standard Gauss-Seidel. Okay, so we can get that. What about random permutations Gauss-Seidel? So this is the variant where you shuffle. You can express that in this notation as well. So what you're doing here is you can think of it as doing a symmetric row and column reordering of the matrix A according to some permutation matrix PL. So after you've done that reordering, you can break the matrix again into these three pieces, lower triangular, upper triangular, diagonal. You can then form the operator for that epoch. It's now going to depend on the permutation, so I've got a subscript L there. And so after L epochs, you've got this kind of complicated looking expression for what the value of x is going to be. So all that's happened is I take the initial x, I shuffle its components, I apply this operator for the P1, and then I unshuffle. I kind of put things back where they were, and repeat that process for each epoch. So this is the closed form expression for what we have after L epochs. So the question is, can I take the expectation of this property of this expression here over these permutations and over whatever distribution I assume for the initial x naught? Well, that's hard. And we were kind of stuck here for a long time because not only does this quantity depend on the PLs, but the CLs depend on the PLs. So the dependence on the permutations is actually very intricate. And so it was, this is quite hard to analyze. However, if you make assumptions about the form of A, you can find some special cases of A for which this becomes tractable. And that's what I'm going to be talking about. Okay. So first of all, before we get to that, I'll just show you a few computations just to show where the differences show up between the different variants of coordinate descent. So this comes from a talk that I gave at ISMP. I'm just going to give a little sample of the results. I just constructed some matrices A by taking a random orthogonal matrix V, a diagonal matrix with where the elements followed a log uniform distribution between 10 to the minus 1 and 1, or 10 to the minus 2 and 1. So this part, you can adjust the conditioning of this part by manipulating this value of sigma. And then I add on this 1-1 transpose matrix, or some multiple of that. And remember, this 1-1 transpose matrix is the one for which L over L max is maximized. Okay? So by cranking up this constant zeta, I can make it more and more like the LL1 transpose. And then I scale this by just some constant to make sure that the maximum diagonal is 1. Okay, so that's how I get test matrices. What do we expect to see? Well, if there's no contribution from that term, we actually find that L over L max is very modest. And so all of the methods behave sort of similarly, steepest descent and all the variants of coordinate descent. And that's what we'll see. But as we start to crank this up, we start to see differences emerge between the different variants. So let's have a look. Here's a very well-conditioned problem. Condition number of A is only about 10. L over L max is only 2, very modest. And you can see that whether we take fixed step lengths or whether we take the optimal step length at every search direction, these methods are not too different from each other. Steepest descent, randomized cyclic or random permutations, fully random. Notice I've got slightly different terminology here, but these are the 3 variants of coordinate descent that I talked about, and this is steepest descent. So they're not too different. When you go to a higher condition number, again, there's not a lot of difference, except steepest descent with a fixed step length is pretty bad, and the coordinate descent methods are all generally better than any version of steepest descent. So this is, again, somewhat intuitive, because the coordinate descent methods are always making use of the latest information about x. And that's showing up, even though it doesn't show up necessarily in the analysis, it's showing up here in the computations. Okay, now when I add on some multiple of that 1-1 transpose matrix, we really start to see differences between the randomized coordinate descent methods, these first 4, and the cyclic method. These are suddenly much faster. And that's partly accounted for by the fact that L over L max is now 50 rather than being 2 or 3 or 4. And also the dimension is worse. So this is somewhat accords with what the analysis is telling us, that the cyclic approach is worse by a factor of n, or n to the 1/2, and it also is worse by a factor of L over L max. So we're really starting to see that show up for this specific kind of matrix. We're also starting to see these methods be better than full steepest descent. So if I zoom in, if I leave out the steepest descent, you really do see the difference between the cyclic variant and the random variants. And notice in particular that the randomized permutation variant is very close in behavior to the fully random variant, whereas the existing analysis suggested it's only as good as the cyclic variant. So it's much better than that. That's what we wanted to understand. And if we really crank up that 1-1 transpose contribution, the differences just become even more stark. Okay, so we can analyze that. In particular, we can analyze the random permutations variant if we consider a special form of the matrix A. So I asked the question, is there any way that we can simplify that big ugly expression that we had for the random permutation variant? Is there some form of A that we can choose that makes this a little bit more tractable? And the answer is yes. If you pick an A to have these properties, it's invariant under symmetric permutations. That is, if I take A and do any random reshuffling of the rows and columns, I just get A back again. Okay? If it has 1s in the diagonal and if it's positive semi-definite, then I can simplify this expression. And the way it simplifies is that the CL no longer depends on the permutation. Because of this property here, when I do the permutation, then break the matrix up and form this operator, the matrix never changes. And so this operator is always the same. So this is simpler than I had a few slides ago, because the CL is all just replaced by a constant C. So the permutations now enter in a much more analyzable way, and it turns out that I can take expectations over these permutations in this expression. So that's what we're going to do. Okay. So Sun and Ye actually homed in on the same matrix independently in early last year, and they were particularly interested in analyzing the cyclic method. They wanted to verify that, in fact, in this case, the cyclic one really is worse, that the iteration complexity does hit its upper bound, and so they proved that this that the bounds that Beck and Tetraishvili got for cyclic coordinate descent were not pessimistic, because there are matrices that really achieve those worst case bounds. As I mentioned, Sun and Ye refined that a little bit, and when they applied it, when you took that ugly expression that they got a few slides back and plugged in this matrix, essentially what they find is that the per epoch convergence is 1 minus some modest factor c times delta over n squared. Delta is the value that goes into defining this matrix, this permutation invariant matrix. So basically, I should have said what this matrix is. It's got ones in the diagonal, and all the off-diagonal elements are 1 minus delta, okay? So it's a very, very simple matrix, parameterized by a single value delta. And this matrix has the property that its biggest eigenvalue is about n times 1 minus delta, and all other n minus 1 eigenvalues are just delta, okay? So it has a very specific structure and properties. So what they showed in Sun and Ye was that they showed that the cyclic coordinate descent has about this per epoch convergence rate. Random coordinate descent, if you plug this into Yuri-Nesterov's analysis, you find that the expected per epoch convergence rate of random coordinate descent is 1 minus delta. So it's much faster than the cyclic rate. In fact, the iteration complexity is about order n squared better. And that's really what we see in practice. Okay. Now what about random permutation? So that was what I was interested in analyzing. So I wanted to take an expectation of this expression. In fact, I wanted to look at the expected function value rather than the expected x value. So I just plug xln into the function and I get this expression here, and I want to take the expectation of that over the p's. I can assume all the p's are IID, they're all chosen independently of each other, and I'm also going to assume that the initial vector x is chosen to have components drawn from normal 0, 1. Okay? So taking the expectation with respect to x naught is easy. It's just the trace of this matrix, essentially. So that part's easy. The hard part is analyzing the expectations over the PLs. Okay, so how do we do that? Well, essentially we do it from the inside out. You can start by taking the expectation with respect to the PL. And you only have to look at these few terms in the middle of the matrix here. And then having done that, you can take the expectation with respect to PL minus 1. And you gradually work all the way out to P1. Okay? So you can do that systematically by defining these matrices A bar T to sort of be the partial expectation starting from PL, going to PL minus 1, down to PL minus T plus 1. So this sort of gives you the intermediate step in working your way out from the middle of the matrix. Okay? And ultimately, when you've worked all the way out to the end, you've taken the expectations with respect to all the permutations, you can get this expected function value by simply taking the trace of the final element in the sequence. Okay? So how do we figure out these guys? Well, first we notice, well, I guess I'll skip ahead a slide. First we notice that they satisfy a recurrence relation. You can get from one A bar T in the sequence to the next by just taking the expectation over a single permutation of this expression here. Okay? So we need to know how to do this. Take the expectation of this over T, over P in order to get from one element to the next. Okay, so how do we do that? And this is where I skip back here. There's this technical lemma. And it says that if I've got any matrix Q, doesn't have to be symmetric or anything, and I'm interested in the expectation of P, Q, P transpose over all possible permutation matrices, that's simply given by some multiple of the identity plus some multiple of the all ones matrix. Okay? So the expectation of the permutations has this homogenizing effect. It sort of takes the diagonal and just averages out all the diagonals and replaces all the diagonals with just their average. Then it takes all the off diagonals and replaces all them by their average. Okay? And these expressions look a little bit complicated, but that's all that's happening, is just an average over the diagonals and a separate averaging over the off diagonals. That's all that's happening. So we use this lemma over and over again in this analysis. Okay? So in particular, what I need, the workhorse for analyzing that very special A that I talked about, is you need to be able to compute the expectation with respect to P of this expression, where Q is equal to C transpose C, and you also need to compute the expectation with respect to this matrix. C transpose the vector of all ones times its transpose, the expectation of that with respect to p. And it turns out both of those have this form, given here in the lemma, and we can write down exactly what the coefficients are, d1, d2, m1, m2, and they're given by these expressions here. And they all depend on this operator, this Gauss-Seidel one epoch operator. So we have to do about 4 pages of analysis to figure out how those all depend on delta and n, and we find that the 4 coefficients depend in this way on delta and n. So not too hard, but a lot of tricky messing around. You can also come up with a closed form expression for the matrix C. It depends on delta. This is the epoch-wise operator. Okay, so back to where we were trying to evaluate the sequence of matrices A bar T from the inside out. We start from the fact that the original matrix that we're working with has exactly this form. It has the form of a multiple of the identity plus a multiple of the all ones. So we can certainly do the first step of going from A bar 0 to A bar 1 using that lemma, using this homogenizing technical lemma. And after we do that first expectation, this form is going to be preserved. The matrix that we get after that first expectation is still a multiple of the identity plus a multiple of the all ones. It's just the coefficients change. Okay? And so what we find is that, here's the argument for going from A bar T to A bar T plus 1. And what it shows is that recursively you can argue that if A bar T has this form, then A bar T plus 1 will have this form with 2 different coefficients. Okay? And in fact, you can generate this very simple 2-variable recurrence relationship which gets you from A bar T to A bar T plus 1. And the matrix is just made up of these 4 coefficients, d1, d2, m1, m2. And so you can figure out what happens to the A bar T simply by looking at what happens to the elements of the sequence of eta and nus. And it's given here. There's no residual term. There's no remainder term. This tells you exactly what's going on. Okay. So, we can just look at what happens over the first epoch. You start out, the initial A has eta equals delta. It's delta times the identity plus 1 minus delta times the matrix of all ones. If you hit it with one phase, with one epoch, the eta coefficient drops, it stays at about delta, and the new coefficient drops to delta. So you get a big improvement just over the first epoch, about a factor of delta improvement if delta is small. And then you can continue to apply that argument to subsequent epochs. You find that after t epochs, you get about m, this matrix m to the power t, times the initial coefficients. And you're able to show that the per epoch improvement is about 1 minus 2 times delta, okay, on average in expectation. And that's very similar to what you get for randomized coordinate descent, fully random coordinate descent. So what we've shown is that for this very special matrix, this invariant under permutations matrix A, that the random permutations variant actually really does provably have the same behavior as the fully random variant. Okay. So something very special happens on the first iteration. This is worth mentioning. Even the very first step, not just the first epoch, but even the very first step gets a very big reduction of a factor of about 1/2 delta. So you actually get most of the reduction in the first epoch actually happens on the very first step. Essentially because it almost projects onto the plane of all ones. And so, right away it decreases. But this analysis that I've shown here tells you what happens from then on, essentially. Okay, and the computations sort of confirm these differences between the 3 variants. This is just a version of this matrix A where delta is 0.05. Condition number is pretty high, about 1,000, 2,000. The cyclic variant here, it's sort of hiding behind the legend, but it's very slow. And the 2 random variants are very similar. And this is completely typical. Regardless of how you choose n and delta, you see pictures like this all the time. You also see the dependence of n showing up. In the cyclic version, as n increases, the convergence gets worse because remember the rate there is 1 minus delta over n squared. So as n gets bigger, it gets slower and slower. Whereas the expressions for the 2 random variants, it doesn't matter what n is. They're always 1 minus delta or 1 minus 2 delta. And you see that here. They're independent of n. Okay, so that matrix is very special, okay, that invariant A matrix. So I wanted to extend that to a slightly more general class. And in fact, most of these differences between the cyclic and random variants can be seen when you've got one dominant eigenvalue. That's the key property in the experiments. And so matrices with one dominant eigenvalue, this is sort of a fairly typical form. It's a small matrix. I've assumed here for simplicity it's the identity, plus a larger multiple of some vector u. Okay. But importantly, it turns out to be important for the analysis that the elements of the vector u are not too different from each other in magnitude. So in the special matrix we were considering, u is just a vector of all ones. So I'm going to relax it and I'm going to say, give me a delta and give me an epsilon, sort of similar in size, both small but similar in size. And now instead of having all ones here, I'm going to say the elements of u in absolute value have to fall in this range. Okay, so it relaxes a little bit what we had for that very special matrix. So if I now assume I'm dealing with a problem with this matrix, I can do a diagonal transformation involving elements of u. I can hit it before and after with u inverse, and I can transform it to this form. And this looks a lot like what I've already been dealing with. In fact, the second term is identical to what I was working with in the invariant A matrix. The first term has changed from being delta times the identity to delta times some other diagonal. But that other diagonal has the form of an identity plus some matrix D, epsilon times some matrix D. Okay. Now the behavior of a coordinate descent applied to this transformed version of this matrix is very similar. So I can work either with the B or the A epsilon, and you can provably get pretty much the same behavior. So I may as well analyze this one because it's a little bit easier to deal with. Okay? So how have I generalized that invariance matrix A? I've just added on epsilon times some matrix D. And if you do experiments with this, you find that even for quite large values of epsilon, this matrix really shows up differences in behavior, the same differences in behavior between cyclic and random versions that we saw for the special matrix. So I really wanted to analyze this case. Okay? And so I spent many hours in the coffee shop across the street trying to derive a recurrence that mirrored what we got in the special case, but appropriately generalized it to the presence of epsilon times D. Okay, so that's what I'm going to do in the last, I guess I got 5 or 7 minutes or so. Okay, so a little bit of notation. D here is diagonal. I'm going to write it as diagonal of a vector D. And there's a couple of quantities here. This is the average size of D. This is the average size of the squares of the elements of D. Okay, so the setup for the analysis, very similar to what we had before. I'm still going to use those matrices A bar T and try to figure out, as I work from the inside out of the expectation, what happens to the expected value of F. Okay, now what's different here is that because we no longer have this invariance under symmetric permutations, the Gauss-Seidel operator does depend on P again. We've gone back to the situation that depends on P. But but the dependence on P isn't too bad because A changes with P only on the diagonal. The off diagonals of A are always 1 minus delta still. So it's just that when you do a symmetric row column permutation, the elements of the vector D just get shuffled around on the diagonal. That's all that happens. And that makes the analysis tractable. Okay, so one epoch looks like this. A shuffle followed by an application of the one epoch operator followed by an undoing of the shuffle. Okay. The setup of the analysis very much the same as before. We have the sequence of matrices A bar. We're going to work from the inside out, so all that part is kind of the same. And the approach is very similar to what we did in the special case. We look for a compact representation of the matrix A that propagates through all the shuffles. So remember in the invariant case we were able to represent A just in terms of 2 parameters, eta and nu. It turns out now we need 7 rather than 2. And the other thing that goes wrong is that we've now got remainder terms getting spit out. So we no longer have a completely exact analysis. We just sort of do it down to order epsilon cubed. And that's not bad because on the first iteration you get on the first epoch you get an order epsilon improvement. So this tells you what happens for a bunch of subsequent epochs. It doesn't go all the way to 0. So it's only an approximate analysis. And cutting to the chase, what we can end up showing is the overall per epoch rate is similar to what you get for the special case, the invariant A. So we can still prove linear rates. Okay, here is the compact representation. So in the special case, we just had these two forms. Now we've got a bunch of other terms. You see the vector and matrix D showing up. You see in different ways. You get a DD transpose, you get a D squared, you get a D, and so on. And so we want to track what happens to these 7 parameters as we go through from one epoch to the next. So again, we want to use that technical lemma, but now we have to apply it to this. We have to take the expectations of this expression, where I plug in the middle here each of these 7 terms. Identity, 1, 1 transpose, D, this guy here, DD transpose, and so on. I have to figure out what this expectation is for each of those 7 terms. So we end up with a 7 by 7 table, okay? And I was still figuring out elements of this yesterday when I was sitting over there. So I only filled this table in at midnight last night. But I actually did a second version of this slide where you can see the whole table, but the font's a little bit smaller. So the rows just show, this is what happened. This is the matrix at the start of the epoch. The columns show what happens after one epoch, what happens in expectation to each of the terms. And the dots mean, well, what happened there was that it only contributed an order epsilon cubed to the final result. So we can ignore what's happening at the dots here. But at the other elements, you get decreases that are not so great. So you have to track what's happening to those. You'll see a bunch of 1s here. So for example, any coefficient of D, after one epoch, it basically stays the same. The same is true of DD transpose, the same is true of a D squared. However, overlaid on all this, there's a factor of 1 minus delta squared. So the true decrease per epoch is 1 minus delta squared times what you see in this table. So that's why you can still get this overall linear rate of roughly what you get in the invariant case. Okay, so if you track what happens over the first few epochs, at the start, these are the values of the 7 parameters, of the 7 coefficients of these 7 terms. Delta 1 minus delta epsilon times D, 0 for all the others. After one epoch, you get some epsilon squared showing up. After a second epoch, to first order, these don't change. The leading terms stay the same. And so essentially after one epoch, you capture most of what's going on. You get some rearrangement of the weight between the different terms. After that, you just get this kind of additional factor of 1 minus delta squared per epoch. And so you end up with a similar overall rate. Now you have to be careful about accounting for subtle differences, the higher order differences between these terms, and these actually have the effect of modifying this rate a little bit, but it's still provably linear. Okay. So that's where we are. Again, we get this phenomenon that on the very first iteration there's a really big improvement. So everything that happens after that is kind of just incremental, slow linear improvement. And I'm actually finishing on time. So what have we done? We've talked about different versions of coordinate descent applied mostly to convex quadratics. We've really drilled down on the issue of how to analyze the fact that the random permutations variant looks a lot like the fully random variant, and we proved that that's true on certain special matrices. I would say, just as a general comment, the random permutations variant is of great interest for stochastic gradient methods. Because that's often how they're implemented. When you're doing stochastic gradient on a bunch of data, you often do a shuffle of the data and then work through them in the shuffled order and periodically reshuffle. That's how a lot of training of deep learning networks is done. But there's very limited results on random permutations. It's very generally easy to analyze the fully random sampling with replacement case. There are only a few papers analyzing that I'm aware of that analyze the random permutations case. And so here we're dealing with coordinate descent rather than stochastic gradient, but I think these are the first results that I know of that are able to prove that random permutations behaves like fully random for coordinate descent. So I'll finish with that. Thank you very much for your attention.